This video will go over a quick justification for output stages, which are also sometimes called power amplifiers, and then cover an important theorem that lends us insight about how to transfer power from an output stage into a load. Appropriately, the theorem is called the maximum power transfer theorem. I've drawn a common emitter here that is DC coupled to a very small load resistance. As you might have discovered in lab, very small load resistances mess with your bias point. In this case, we know the highest voltage we could possibly get at the output node will occur if the transistor is in cutoff. And that output voltage still won't be very high because it's set by a voltage divider between 2 kiloohms and 10 ohms when the transistor is not conducting any current. So in fact, if this load is small enough, once we turn the transistor back on, it might not be able to leave saturation, so we may never get our circuit into forward active. Okay, so we've fixed this sort of DC problem before by AC coupling our loads, right? That's how we've been measuring our output resistance, for instance. So why wouldn't that work here? So I guess it would, in the sense that our collector voltage would become independent of the voltage of our load at DC. However, the small load still limits the gain, because it will appear in parallel with our collector resistance in a small signal model. So it's not clear that we'd be faithfully driving the V-in signal onto the load. Also, if we have a coupling cap, our power transfer will become into the load, will become dependent on frequency, and often somewhat inefficient, which we'll talk about more on the next slide. So AC coupling overall doesn't work great when we're trying to deliver power to a small load. And it's worth mentioning that this idea of driving a small load isn't an academic problem. There are lots of tiny weird loads in the world, like motors, speakers, plasmas, antennas, heaters, and many others. So we need to come up with an amplifier that can drive these physical things. Because there are so many weird loads in the world, it's worth making a unified theory to figure out how to get power into them. The theoretical tool that we use for that is called the maximum power transfer theorem, and we'll drive it using the circuit pictured here. Before we begin, I need to make two caveats. First, we're going to do this analysis using real resistors because that's the most familiar material in this class. However, there's an extension of this that tells us more information about reactive loads and reactive source impedances. And second, we're analyzing a linear system here, right? This is just two resistors. But we build amplifiers out of transistors which are wildly nonlinear. And even worse, we won't be able to use our usual dodge of retreating to small signal analysis to make our amplifiers appear linear, because we want output stages to deliver really high power. And delivering really high power usually means really big voltages and really big currents, so small signal analysis won't work well. However, you can still get a little bit of insight or ballpark estimates from small signal analysis. For instance, if you want to know, like, oh, what's the lowest output impedance I have, you might calculate at the peak of your current waveform. So as a result, we can still get a little bit of insight from the max power transfer theorem, and it's a good thing to know. We start by figuring out how much power is dissipated in the load. Because the load is resistive, that means the load voltage squared over RL tells us the power dissipated in it. The load voltage here is expressed as a voltage divider times the source voltage. We can substitute in our expression for the source voltage with this 0 to peak amplitude and rearrange the resistances a little bit to get this expression. Doing so reveals that the power is a function of time, specifically this sine squared of omega t. We almost always care about the time averaged power instead of the instantaneous power. There are a few situations where instantaneous power will violate transistor maximum value, but time averaged power, for instance, determines how hot the load gets. So taking the time average of this converts sine squared omega t into a factor of 1/2. which is a fact you should memorize. By the way, I indicate time averages by using these brackets around a variable. Awesome, so we have this expression for power in the load. Let's see what we can do with it. We know that we want PL to be as big as possible, but there are two scenarios we have to consider. In the first, we control the source resistance, but not the load. So just looking at this expression for PL, our source resistance only appears in the denominator, so we know we'd maximize our load power by setting source resistance to 0. The other situation we have to consider is where we control the load. By the way, we don't have to consider a situation where we control both the source and the load, because then we just do whatever we want. Because RL appears in both the numerator and the denominator of our PL expression, we have to find the maximum value by taking a derivative of the power and the load with respect to RL. And I've done so here. We can simplify that expression a bit in order to get everything over the same denominator, this RS plus RL cubed. And that tells us that we'll get a maximum when these two numerators add to 0. And that algebra is easy enough. This RL cancels with one of those two RL, and we find that we maximize our power transfer when our load resistance is equal to our source resistance. So awesome. So now we know both how to send and receive power. We send it by making our source resistance 0. We receive it by making our load resistance equal to the source resistance. Since we're building amplifiers, we're mostly in the business of controlling source resistances. So the big insight we can get here is that we should design amplifiers that have very low output resistances. Now, the fact we're dealing with large signals complicates that message a bit, since output resistances change with our bias point, but it's a good starting point to figuring out what an output stage might look like. For instance, we might say, let's start with an emitter follower. Those have low output resistances. One final note, efficiency is a very fundamental measure of power transfer. It's the ratio of power delivered to the load divided by power pulled from the source. And you might wonder what the maximum efficiency of a matched power delivery network looks like. The answer is pretty bad, because RS is equal to RL when we have maximum power transfer. We know that the voltage to the load is half the source voltage. Squaring that gives us a peak efficiency of 1/4. So in summary, we need special circuits to drive small loads, strange impedances, or lots of current. These are called power amplifiers or output stages. We maximize power transfer from a source to a load by minimizing the source resistance or matching the load resistance to the source. Efficiency is denoted by this symbol eta, and it's the power in the load over the power in the source. And high power circuits require large signal analysis.